Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Our star, though seemingly constant, is a churning cauldron of nuclear fusion and magnetic energy. Sitting just 8 light minutes away, the Sun bathes Earth in the energy that powers all life, but it occasionally reminds us of its awesome, destructive potential. Solar flares and coronal mass ejections, massive eruptions of energy and magnetized plasma, regularly burst from the Sun's surface, casting waves of charged particles into space. While most pass harmlessly, some are directed at Earth with consequences that range from beautiful auroras to potential catastrophe. On September 1, 1859, British astronomer Richard Carrington was routinely sketching sunspots when he witnessed a blinding flash, what would later be known as a solar flare. Within 17 hours, telegraph systems worldwide went haywire. Operators reported receiving electric shocks, papers caught fire, and some systems continued working. Even when disconnected from power sources, the Carrington event remains the most powerful geomagnetic storm in recorded history. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. What many don't realize is that the 1859 storm happened during a relatively quiet solar period. Had such an event struck our modern, technology-dependent civilization, the consequences would be catastrophic, as Dr. Miho Janvier of the Institute for Space Astrophysics explains. The Carrington event today would affect far more than telegraphs. It would potentially disable satellite networks, power grids, and electronic systems continent-wide. What exactly causes these solar tantrums? Deep within the Sun, a dynamo effect creates a powerful magnetic field. This field becomes twisted and contorted as different parts of the Sun rotate at different speeds. Think of a rubber band being twisted tighter and tighter. Eventually, something has to give. When magnetic field lines snap and reconnect, they release tremendous energy in the form of solar flares and coronal mass ejections. Solar flares are classified on a logarithmic scale, A, B, C, M, and X, with each letter, representing a 10-fold increase in energy output. The most powerful flares fall into the X-class category. The Carrington event is estimated to have been an X45 flare, tens of times more powerful than anything we've measured in the modern era. These measurements come from instruments like the Geostationary Operational Environmental Satellites, GERS network, which continuously monitors the Sun's X-ray emissions. When these instruments detect a significant flare, they trigger an alert system that warns of potential impacts. Our planet has natural defenses. Earth's magnetic field, the magnetosphere, deflects many charged particles around our planet rather than through it. This same mechanism creates the shimmering curtains of auroras near the poles when some particles do penetrate the outer atmosphere. But as powerful as Earth's magnetic shield is, it has vulnerabilities. The magnetosphere is compressed on the sun-facing side and extends into a long tail on the opposite side. When a coronal mass ejection hits with the right magnetic orientation, it can effectively connect with Earth's magnetic field in a process called magnetic reconnection, allowing particles to pour in through the poles. The 11-year solar cycle means periods of increased solar activity, called solar maximum, occur regularly. During these times, the frequency of flares and coronal mass ejections increases dramatically. We're approaching the peak of solar cycle 25 now, expected to reach its maximum between 2024 and 2025. Some solar physicists have raised concerns that we're overdue for another Carrington-level event. While small to medium flares occur regularly, statistics suggest a 1 to 2% chance per year of experiencing a flare of similar magnitude to the 1859 event. Those odds might seem small until you consider the potential consequences. As Dr. Daniel Baker of the Laboratory for Atmospheric and Space Physics bluntly states, modern civilization depends on a technological infrastructure that simply didn't exist when the last extreme solar storm struck. This infrastructure, our electrical power systems, communications networks, and transportation systems, has vulnerabilities that could transform a major solar event from inconvenience to catastrophe. Power grids represent perhaps the greatest concern. Long-distance transmission lines act like antennas for geomagnetically induced currents. When a coronal mass ejection impacts Earth's magnetosphere, it causes rapid fluctuations in the geomagnetic field. These fluctuations induce powerful electric currents in conductors, including power lines, that can overwhelm transformers and cause cascading failures. High-voltage transformers are particularly vulnerable. These massive, custom-built devices regulate power across the grid. When saturated with geomagnetically induced currents, their internal windings can overheat and melt within minutes. Modern transformers are often pushed to operate at near capacity to meet growing power demands, leaving little margin for additional stress during geomagnetic events. Manufacturing replacement transformers isn't simple. Each is custom designed. For its specific location, weighs hundreds of tons and typically takes 1 to 2 years to build. The Department of Homeland Security estimates that a severe solar storm could damage or destroy 300 to 400 high-voltage transformers in the United States alone, potentially leaving 130 million people without power for months or even years. In March 1989, a moderate geomagnetic storm, far less powerful than the Carrington event, struck Quebec's power grid. Within 90 seconds, the entire province lost electricity as protective systems triggered cascading shutdowns. 6 million people were left without power for 9 hours during sub-freezing temperatures. The same storm damaged a 400-ton transformer at a nuclear plant in New Jersey and caused anomalies in power systems across North America. Satellites represent another vulnerable system. In low Earth orbit, satellites would face increased atmospheric drag as the upper atmosphere heats and expands during a severe solar event. Communications, navigation, and reconnaissance satellites in higher orbits face direct bombardment from energetic particles that can damage solar panels, corrupt onboard computers, and disable sensitive electronics. In 2022, SpaceX lost 40 satellites to a relatively minor geomagnetic storm when the resulting atmospheric expansion increased drag by 50 to 60%, preventing the satellites from reaching their operational orbits. For high-precision systems like GPS, disruption would cascade through countless dependent systems, from emergency services to financial transactions. International air travel would face significant disruptions. Commercial flights traversing polar routes, common for intercontinental journeys, would be diverted or grounded to protect passengers and crew from increased radiation exposure. Communications blackouts would disrupt air traffic control, potentially affecting thousands of flights. Globally, our reliance on networked technology creates additional vulnerabilities. Banking systems, supply chains, and basic utilities all depend on continuous communications and precise timing signals. GPS satellites provide the latter, synchronizing everything from cellular networks to financial transactions with nanosecond precision. Without this timing infrastructure, many systems would gradually drift out of sync and eventually fail. Dr. Catherine Strong of the National Oceanic and Atmospheric Administration, NOAA, Space Weather Prediction Center explains, the interconnected nature of modern infrastructure means failures can cascade across systems. Power loss affects communications, which impacts transportation, which disrupts supply chains, creating a domino effect that could paralyze regions or even continents. Perhaps most concerning is that these vulnerabilities disproportionately affect developed nations. The more technologically advanced a society becomes, the more susceptible it grows to space weather events. Countries with older or less developed infrastructure might, paradoxically, weather such storms with fewer disruptions than their more advanced counterparts. For context, the 2023 global semiconductor market was valued at over $550 billion, representing critical components in virtually every electronic device. A severe solar storm could potentially damage semiconductor manufacturing facilities, which require uninterrupted power and precise environmental controls. The resulting chip shortage would dwarf the supply chain issues experienced during the COVID-19 pandemic. While the Carrington event stands as the benchmark for extreme solar storms, history reveals other significant space weather events that offer crucial insights into what we might face. Each provides valuable data points in understanding the frequency and potential severity of these stellar outbursts. In May 1921, a geomagnetic storm comparable to the Carrington event struck Earth. Though less famous than its 19th-century predecessor, this storm caused telegraph disruptions worldwide and sparked fires in several signal stations. The New York Railroad storm, as it came to be known, created auroras so bright that they cast shadows at midnight and were visible as far south as Texas and California. Newspapers reported that people in New York could read the newspaper just by the light of the aurora. Modern analysis suggests this event may have been nearly as powerful as the Carrington event. More recently, August 5, 1972, saw a solar flare trigger an immense coronal mass ejection that detonated naval mines off the coast of Vietnam. Records from the U.S. Navy indicate that dozens of sea mines, designed to detonate only in response to magnetic signatures from passing ships, were triggered by the geomagnetic disturbance. Fortunately, this occurred in a limited theater of operations, rather than across global military installations. Historical records from East Asian astronomers reveal a massive red aurora in September of 1159 that covered much of the planet. Chinese court astronomers wrote, "A rainbow of blood-red light spanned the sky from the south to the north." Japanese observers noted that the sky was as bright as day throughout the night, while Korean records describe a flame that filled the entire northern sky. Similar descriptions appear in European and Middle Eastern accounts from the same period. Studying tree rings and ice cores has allowed scientists to detect even more ancient events. Carbon-14 isotopes embedded in ancient trees and beryllium-10 deposits in ice layers serve as proxies for solar activity. These records suggest a solar storm in 774 CE that was potentially stronger than the Carrington event. The same methodology indicates another massive event around 561 BCE. Dr. Pascal Rosenblatt of the Royal Observatory of Belgium explains, "What's concerning isn't just the magnitude of historical events, but their apparent randomness. Major solar storms don't follow predictable patterns. They can occur during solar minimum or maximum, and their strength doesn't necessarily correlate with the overall intensity of a solar cycle." The Quebec blackout of 1989 demonstrated the vulnerability of modern power grids to even moderate storms. What's often overlooked is that the same storm nearly caused a similar blackout in the United Kingdom. Only the timing of the storm's arrival, coinciding with lower power demand during night hours, prevented a similar cascade of failures across Britain's national grid. In October 2003, during the declining phase of solar cycle 23, an unexpected series of 17 major flares erupted from sunspot region 10486. Known as the Halloween storms, these events damaged 28 satellites, knocked out power in parts of Sweden, and forced airlines to divert flights from polar routes due to radiation concerns. Astronauts aboard the International Space Station had to seek shelter in more heavily shielded portions of the station. More recently, July 23, 2012 saw Earth narrowly miss what NASA scientists have called a Carrington-class coronal mass ejection. The eruption crossed Earth's orbital path just 1 week after our planet had passed through that region of space. Had it occurred just 9 days earlier, we would have experienced a direct hit from one of the most powerful solar storms in recorded history. That was a sobering moment for the space weather community, recalls Dr. Liang Zhang of the Space Weather Prediction Center. We just had a near miss with a potentially civilization-altering event, and most of humanity remained completely unaware. Each historical event adds to our understanding of solar storm frequency. Current estimates suggest Carrington-level events occur roughly once every 100 to 150 years, meaning we may be statistically overdue. Lesser but still severely damaging storms might occur every 20 to 30 years. What makes forecasting difficult is that, unlike terrestrial weather systems that develop over days, solar eruptions can occur with just minutes of warning. While we can monitor active regions on the Sun, predicting exactly when and with what magnitude an eruption will occur remains challenging. Humanity has developed an impressive array of technologies to monitor our tempestuous star. Our first line of defense against solar threats lies 93 million miles away at the Sun-Earth Lagrange Point 1, L1, a gravitational balance point where spacecraft can maintain position between Earth and Sun with minimal fuel. At this strategic location sits the Solar and Heliospheric Observatory, SOHO. Launched in 1995 as a joint mission between the European Space Agency and NASA, SOHO has revolutionized our understanding of solar dynamics, providing continuous observation of the Sun's atmosphere, magnetic fields, and solar wind. Its coronagraph, an instrument that creates an artificial solar eclipse, allows scientists to observe the Sun's outer atmosphere and detect coronal mass ejections as they erupt. Joining SOHO at the L1 point is the Advanced Composition Explorer, ACE, which provides real-time measurements of solar wind parameters. Dr. Juliana Scheiman of the University of Michigan explains, ACE gives us approximately a 20 to 60-minute warning before solar wind disturbances reach Earth, critical time for power grid operators and satellite controllers to implement protective measures. The Solar Dynamics Observatory, SDO, launched in 2010, orbits Earth while continuously monitoring the Sun across multiple wavelengths. Its instruments can detect changes in the Sun's magnetic field that often precede solar flares, potentially providing hours of advance warning for some events. The Parker Solar Probe, launched in 2018, has ventured closer to the Sun than any previous spacecraft, passing within 4 million miles of the solar surface, a region where temperatures exceed 1 million degrees Celsius. Parker is literally touching the Sun, explains Dr. Noor El-Kadiri of the Harvard-Smithsonian Center for Astrophysics. It's teaching us about the fundamental physics of solar eruptions at their source. Ground-based observatories complement these space assets. The Global Oscillation Network Group, GONG, consists of 6 solar telescopes strategically positioned around Earth to provide continuous solar observation regardless of Earth's rotation. These instruments use helioseismology, the study of sound waves traveling through the Sun, to map conditions below the solar surface where many eruptions originate. The National Science Foundation's Daniel K. Inouye Solar Telescope in Hawaii, which saw first light in 2020, provides unprecedented detail of the Sun's surface. With a 4-meter primary mirror, it can resolve features as small as 18 miles across on the solar surface, equivalent to seeing a quarter from 25 miles away. Converting these observations into actionable predictions falls to organizations like the Space Weather Prediction Center, SWPC, operated by the National Oceanic and Atmospheric Administration. The center maintains a 24/7 watch on solar activity, issuing alerts and forecasts through a familiar scale: R for radio blackouts, S for solar radiation storms, and G for geomagnetic storms. Each uses a 5-point scale, with G5 representing the most severe geomagnetic storms, Carrington-class events. We've developed models that can predict how coronal mass ejections will propagate through the solar system, explains Dr. Victor, Erepetian of NASA's Goddard Space Flight Center. But just as with hurricane forecasting, there are inherent uncertainties. We can predict that a storm is coming and estimate its general strength, but precise timing and impact remain challenging. International cooperation has become essential for effective space weather monitoring. In 2022, the International Space Environment Service linked 24 nations in a global space weather monitoring network. This system enables continuous data sharing and provides redundancy in case individual detection systems fail during a severe event. Commercial enterprises have also entered the field. Companies like Selectria and Space Weather Technologies now provide specialized forecasting services to industries particularly vulnerable to solar storms, such as electrical utilities, airlines, and telecommunications providers. Despite these technological advances, significant gaps remain. Our ability to monitor the far side of the Sun, which rotates completely every 27 days, remains limited. A potentially threatening active region can emerge, develop and build energy without detection until it rotates into view. To address this blind spot, NASA and the European Space Agency have proposed missions to position spacecraft at the Sun-Earth. Lagrange points 4 and 5, 60 degrees ahead and behind Earth in its orbit. From these vantage points, we could observe solar activity across the entire solar disk, providing truly comprehensive monitoring. Perhaps the most ambitious proposal comes from the European Space Agency's Vigil mission, formerly called Lagrange, which would position a dedicated spacecraft at the Sun-Earth L5 point to provide side-viewing imagery of solar eruptions as they travel toward Earth. This perspective would dramatically improve predictions of whether coronal mass ejections will hit Earth and with what orientation, critical information for assessing potential impact. As awareness of solar threats has grown, engineers and policymakers have developed strategies to protect vulnerable systems. These range from operational procedures that can be implemented during warnings to fundamental redesigns of critical infrastructure components. For electrical grids, the most direct protection involves installing blocking devices called capacitors at key transformer stations. These devices prevent geomagnetically induced currents from flowing through transformers while allowing normal power flow to continue. According to the Electric Power Research Institute, retrofitting the U.S. grid with these devices would cost between $200 million and $500 million, substantial but far less than the estimated $2 trillion economic impact of a prolonged nationwide blackout. The challenge isn't technological, it's economic and political, explains Dr. Teresa Liu, who served on the National Academy of Sciences Committee on Grid Security. Utilities operate with tight margins and regulatory constraints. Investing in protection against low-probability events, even catastrophic ones, often falls below more immediate priorities. Some utilities have implemented operational mitigations. When space weather warnings indicate an incoming coronal mass ejection, they can reduce power loads, adjust transmission paths, and increase reserve generation capacity. During the 23 Halloween storms, PJM Interconnection, the largest grid operator in North America, implemented such measures, successfully preventing equipment damage across 13 states. Satellite operators have developed their own protective strategies. When warned of incoming solar storms, they can place satellites in safe mode, shutting down non-essential systems and orienting solar panels to minimize damage. Newer satellites incorporate radiation-hardened components, redundant systems, and autonomous recovery procedures designed to withstand all but the most extreme solar events. The Global Positioning System represents a particular vulnerability given its critical role in modern infrastructure. Its $50 billion replacement, GPS-3, incorporates significantly improved radiation shielding, signal strength, and accuracy. Each satellite in the constellation can operate autonomously for up to 60 days if ground control becomes unavailable, a critical feature during extended solar emergencies. Aviation has implemented its own protective measures. The Federal Aviation Administration's Space Weather Program provides real-time alerts to airlines, allowing flights to divert from polar routes during solar radiation events. Modern aircraft incorporate increasing levels of radiation shielding and electromagnetic protection for critical avionics systems. For telecommunications, fiber optic cables offer inherent protection against electromagnetic disturbances compared to copper lines. However, the repeater stations that amplify signals along these cables remain vulnerable to power disruptions and electromagnetic interference. Companies like AT&T and Verizon have invested in backup power systems designed to maintain communications during extended outages. On an individual level, preparedness remains uneven. A 2022 survey by the Federal Emergency Management Agency found that while 84% of Americans had basic preparations for weather-related emergencies, fewer than 20% had considered space weather in their emergency planning. There's a disconnect between professional awareness and public understanding, notes Dr. Michio Katsumata of the International Association for Emergency Preparedness. Most emergency managers now include space weather in their planning scenarios, but public education efforts have been limited. The Department of Homeland Security's 2018 National Space Weather Strategy and Action Plan marked a turning point in governmental approaches to the threat. The plan established clear roles for 24 federal agencies, funded improved forecasting capabilities, and mandated vulnerability assessments for critical infrastructure. These efforts accelerated after the 2019 Executive Order on coordinating national resilience to electromagnetic pulses, which explicitly included solar storms as a threat requiring coordinated preparation. The order mandated improved forecasting, vulnerability assessment, response planning, and protective standards across 16 critical infrastructure sectors. International coordination has similarly evolved. The United Nations Committee on the Peaceful Uses of Outer Space established the Expert Group on Space Weather in 2020, formalizing international cooperation on monitoring, forecasting, and response planning. The World Meteorological Organization now coordinates global observation assets, ensuring continuous monitoring regardless of national budget cycles or changing priorities. What's encouraging is the shift from seeing space weather as an exotic threat to recognizing it as a manageable risk, observes Dr. William Patterson of the Space Weather Prediction Center. We've moved from asking if we should prepare to methodically addressing how we prepare, with increasingly specific and actionable plans. Yet challenges remain, particularly for developing nations where basic infrastructure needs often outweigh concerns about solar threats. The International Space Environment Service has established capacity-building programs to help these nations implement cost-effective monitoring and protection measures appropriate to their technical capabilities. And resource constraints. What would happen if a Carrington-class event struck tomorrow? The cascading effects would unfold across hours, days, and potentially years, testing social and economic resilience on an unprecedented scale. Within minutes of a major solar eruption reaching Earth, satellite communications would begin experiencing disruptions. GPS accuracy would degrade significantly, affecting navigation systems worldwide. High-frequency radio communications, still used by aircraft over oceans, would become unreliable or impossible as the ionosphere absorbed solar energy. Within hours, geomagnetically induced currents would begin flowing through power grids. Despite protective measures, transformer failures would occur in the most vulnerable regions, typically higher latitudes, with underlying igneous rock formations that prevent current from easily flowing through the ground. Cascading failures could plunge entire continents into darkness. Dr. Richard Anderson of the National Infrastructure Simulation and Analysis Center explains, "Our models suggest that in a worst-case scenario, up to 70% of the U.S. population could lose power for periods ranging from weeks to months. Recovery times depend largely on transformer damage and availability of replacements. The immediate human impacts would be severe but manageable in most regions. Modern hospitals maintain emergency generators with fuel reserves, typically lasting 72 to 96 hours. Critical facilities like water treatment plants similarly maintain backup power, though with varying capacities and readiness. The secondary effects would prove more challenging. Without electricity, fuel pumps at gas stations wouldn't operate, limiting transportation and generator refueling. Electronic payment systems would fail, forcing a return to cash transactions complicated by inoperable ATMs. Cell phone networks would gradually fail as backup batteries at towers depleted, typically within 24 to 48 hours. The most immediate threat to human life would come from interruptions to heating and cooling systems, notes Dr. Eliza Worthington, who studies infrastructure resilience at Stanford University. A winter storm coinciding with power loss could create life-threatening conditions across northern regions, while summer heat waves would pose similar risks in southern areas. Food security would become a concern within days. Modern grocery stores typically maintain just 3 to 5 days of inventory under normal purchasing patterns. Without refrigeration, significant food spoilage would occur within 48 hours. Agricultural production would face disruptions from inoperable irrigation systems, automated feeding systems, and transportation limitations. The economic impact would be staggering. A 28 Lloyds of London study estimated that a Carrington-level Event could cause up to $2.6 trillion in damages to the US economy alone, approximately 13% of GDP. Global impacts would likely exceed $10 trillion. Recovery would follow distinct phases. Initial emergency response would focus on maintaining essential services, hospitals, water systems, and emergency communications, using mobile generators and fuel reserves. Military assets would likely be deployed to support civilian authorities, particularly for maintaining order in urban areas and distributing essential supplies. The second phase would involve temporary restoration of regional power islands, smaller sections of the grid that can operate independently. Areas surrounding hydroelectric facilities offer particular advantages, as they can often restart without external power sources. Nuclear plants, which comprise about 20% of US electricity generation, would face particular challenges, requiring external power to safely restart after emergency shutdowns. The real bottleneck comes in Phase 3, the replacement of damaged transformers, explains Dr. Johanna Mendez of the Electric Power Research Institute. Even with accelerated manufacturing and global coordination, replacing hundreds of custom-built, high-voltage transformers could take years. We simply don't maintain that level of spare capacity. International cooperation would become essential. Countries less affected by the geomagnetic storm would likely provide equipment, expertise, and humanitarian assistance to harder-hit regions. Military transport aircraft would be pressed into service, moving replacement transformers and other critical equipment. The social impacts of prolonged recovery remain difficult to predict. Historical analogies provide limited insight, as no modern society has experienced infrastructure disruption of this magnitude and duration. Studies of regional disasters suggest community cohesion often strengthens during initial response phases, but faces increasing strain as recovery extends beyond expectations. What keeps emergency planners awake at night isn't the technical challenges of recovery. Those are substantial but solvable, observes former FEMA Administrator Michael Rowland. It's the potential for cascading social disruption if recovery timelines stretch from months into years, especially in regions where preparedness is minimal. Against this sobering backdrop, resilience planners have developed increasingly sophisticated recovery strategies. The North American Electric Reliability Corporation now maintains a strategic transformer reserve, with pre-positioned replacements at secure locations across the continent. The Department of Energy's RECX program has demonstrated rapid transformer replacement techniques, reducing installation time from weeks to days. International agreements have established frameworks for emergency resource sharing during catastrophic events. The 2021 International Space Weather Response Compact, signed by 17 nations representing 60% of global GDP, provides mechanisms for coordinated response to severe space weather events, including expedited border procedures for emergency equipment and personnel. As we confront the reality of solar threats, scientists and engineers are developing next-generation technologies to better predict and mitigate these stellar tempests. These advances may determine whether future solar storms become footnotes in history or defining catastrophes of the 21st century. Machine learning represents perhaps the most promising frontier in solar forecasting. Traditional prediction models struggle with the complex, non-linear dynamics of solar behavior. Artificial intelligence systems, however, can identify subtle patterns invisible to conventional analysis. The solar flare prediction model, developed by researchers at Stanford University and NASA Ames Research Center, now achieves 78% accuracy in predicting X-class flares within a 48-hour window, a significant improvement over the 55% accuracy of conventional models. We're teaching algorithms to recognize precursor patterns in solar magnetic fields that typically precede major eruptions, explains Dr. Aisha Nomura, who leads the Stanford project. The system continuously improves as it ingests more data, learning from each solar cycle. Quantum computing may further revolutionize prediction capabilities. IBM's Quantum Research Division has partnered with the Space Weather Prediction Center to develop models that can simultaneously track thousands of variables affecting solar behavior. Early results suggest Quantum-enhanced forecasting could extend reliable warning times from hours to days for major events. Crucial extra time for implementing protective measures. In space, new monitoring capabilities are transforming our solar surveillance. The European Space Agency's Vigil mission, scheduled for launch in 2027, will provide the first dedicated side view of solar eruptions aimed at Earth. From its position at Lagrange Point 5, Vigil will track coronal mass ejections along their entire journey to Earth, dramatically improving arrival time and impact predictions. NASA's proposed Solar Sentinels mission would create a constellation of spacecraft at various distances from the Sun, providing three-dimensional monitoring of solar wind and coronal mass ejections. This distributed approach would significantly reduce false alarms while providing more precise impact forecasts. For protecting Earth's infrastructure, superconducting technologies offer intriguing possibilities. Superconducting power cables, which lose virtually no energy during transmission, could replace portions of the existing grid. Their inherent resistance to geomagnetically induced currents would provide built-in protection against solar effects. While currently limited by the need for extreme cooling, room-temperature superconductors, a holy grail of materials science, would revolutionize grid resilience if successfully developed. Energy storage systems represent another promising defense. Grid-scale batteries, pumped hydro facilities, and emerging technologies like gravity storage could maintain essential services during solar-induced outages. The rapid decrease in battery costs, 90% since 2010, has made emergency storage increasingly economical. Princeton University's Net Zero America project estimates that deploying sufficient battery capacity to maintain critical services during extended outages would cost approximately $140 billion, substantial but manageable when viewed as national infrastructure investment. Autonomous systems could maintain critical functions during solar emergencies. Self-healing grid technologies can automatically isolate damaged sections and reroute power to maintain service. The Defense Advanced Research Projects Agency's RADIX program has demonstrated microgrids that can operate independently during widespread outages, maintaining power to critical facilities like hospitals and water treatment plants. Internationally, space weather has increasingly become a focus of diplomatic cooperation, transcending geopolitical tensions. Even nations with significant political differences recognize the shared threat posed by extreme solar events, notes Ambassador Lynn Rodriguez, who coordinated international participation in the 2023 Space Weather Defense Exercise. It's one of the few threats that truly affects all nations equally. This cooperation extends to capacity building in developing nations. The World Meteorological Organization's Space Weather for All initiative has established regional forecasting centers in Brazil, Egypt, and Indonesia, expanding global monitoring capabilities while ensuring all nations have access to early warnings. Regardless of technical capacity, public education efforts have similarly accelerated. The American Red Cross now includes space weather in its emergency preparedness materials. Japan's Disaster Management Agency conducts annual space weather drills alongside earthquake and tsunami exercises. Finland, particularly vulnerable due to its high latitude, requires all students to complete space weather awareness training as part of secondary education. For individual preparation, technologies like Faraday bags, protective containers, that shield electronic devices from electromagnetic pulses have entered mainstream consumer markets. Home resilience systems now frequently integrate solar panels with battery storage and electromagnetic shielding, providing protection against both conventional power outages and solar events. Despite these advances, fundamental questions remain about our solar future. Solar cycle 25, now approaching its peak, has exceeded predictions in both sunspot numbers and flare activity. Long-term solar behavior remains imperfectly understood, with some models suggesting we're exiting an extended period of relatively benign solar activity that has persisted throughout modern human history. As Dr. Catherine Way of the Royal Observatory, Greenwich observes, the sun we've studied for the past century may not represent its typical behavior over longer timescales. Ice core and tree ring records suggest periods of significantly more intense solar activity in the distant past. We may need to prepare for a more active solar future. Whatever that future holds, humanity's relationship with our star continues to evolve. Once worshipped as a deity, later understood as a nuclear furnace, we now recognize the sun as both the giver of life and a potential threat to our technological civilization. Our growing awareness of solar threats represents not a reason for fear but rather a call to prudent preparation, ensuring that when the next great solar storm arrives, as it inevitably will, human ingenuity will have anticipated its challenge.